Hey guys, welcome back. This is our final lesson of the school year. Um, yeah, make sure that you are turning everything in that you haven't done, um, whether I've put it in the gradebook as missing or not. Just cover your bases because there are a lot of assignments that I haven't put in that I will put in. So anything from the e-learning phase that you have not done, do so, especially if you have a borderline grade or have a chance of going up. Um, do that by Tuesday morning when this assignment is due, and that'll give me a couple days to get grades caught up for late work and whatnot because they're due next Friday, so a week from tomorrow. So anyway, let's get on with our last chemistry lesson, and we have kind of abbreviated, obviously, our acids and bases unit here. There's a lot more that we normally put in, but I'm trying to give you guys the basics. So I think if you were to take a chemistry class in college, which hopefully many of you end up doing at some point, or even an AP Bio or whatever, you've seen this stuff before. So one very important type of reaction that we haven't talked specifically about to this point in acids and bases is called a neutralization reaction. And neutralizing is just what it sounds like. You're putting together acid and base to make a product. It's not always a neutral product, and we're not going to really have time to get into that. But it'll definitely be closer to neutral than what we had with just an acid in the beaker or just a base in the beaker. When we add acid to base, we get closer to neutral, of course. Now, the cool thing about a neutralization reaction is it's actually, if you look at it, it's actually just really a double replacement reaction. So if you look at what's happening here, um, we have a positive H and a negative Cl. Over here, we have a positive Na and a negative OH, and they're just trading partners. They're just trading places, and that's what's going to give you the salt and the water on the other side. So it's a double replacement reaction. It doesn't form a precipitate, but if you remember, one of the details of double replacement reactions first semester when we talked about it was that it either forms a precipitate or a molecule. And of course, water is a molecule. So this is definitely a reaction. So let's take a look at predicting another one. Let's say instead of these two, let's put together, let's say magnesium hydroxide, and let's go with, you guys remember what that would be called? If it's hydrogen phosphate, what is the acid name? Phosphoric acid. Very good. Very good. Okay, so we're going to have a double replacement reaction, and the magnesium and the hydrogen are going to trade places. So that's going to give us magnesium phosphate. And we are going to balance the charges. Magnesium is +2, phosphate is -3, so I'm going to have 3 magnesiums and 2 phosphates, and I'm also going to produce a water. Okay. Now, before we go any further, with ionization equations, when we had a polyprotic acid, we have an acid that has more than one hydrogen. We only remove one of the hydrogens and give it to water. This is different. This is not an ionization equation. So all of the hydrogens are going to be taken off of that acid. So if that threw you a little bit at first, when I just wrote the phosphate over here with the magnesium and I took away all 3 hydrogens, that's how it's going to be when an acid reacts with a base. Not how it's going to be when an acid reacts with water, which is just an ionization. There you would just have 1 hydrogen at a time removed. Okay, in terms of balancing, probably want to balance, I don't know, magnesium first. So a 3, and then balance, if I balance phosphate, I need a 2. And then hydrogen-wise, I've got 3 times 2 is 6 here, plus 2 times 3 is 6 there. So that's 12, so I need 6 there, right? And that's going to automatically balance my oxygens, 6 there, and 6 there, of course, not counting phosphate. Okay, so that is a neutralization reaction. Very simple, and really you've already done it. We're going to use neutralization reactions to do a titration. A titration is just an experimental determination of concentration of one solution by neutralizing it with the solution of known concentration. And unfortunately, we're not going to be able to do any titrations. We usually do like 2 or 3 of these in the lab. So you're not going to have the experimental experience, but what it would look like is, so I've got a picture here, um, and essentially, for example, if you have an acid in a flask, Erlenmeyer flask here, so this is HCl, so they've got it labeled H plus, just because it's an acid. Um, and then we have a base in this long, slender little piece of glassware called a burette. So a burette is basically like it's a giant volumetric measuring device that allows you to drop in a little bit of a liquid at a time, or aqueous solution at a time. And so what we're doing is we know the concentration of the base, we don't know the concentration of the acid, and so we add, so we know the volume of the acid, and what we do is we add the known base to the unknown acid, or the unknown concentration of acid, until we get a neutral pH, and that's going to tell us that the reaction is finished, or at least until we reach what's called the equivalence point. It may not be exactly neutral, but again, we don't really have time to get into that, so we'll just call it neutral. What it looks like is you put an indicator in the acid. In this case, they used phenolphthalein. In the presence of an acid, phenolphthalein is clear. Yes, I said that right. In the presence of an acid, phenolphthalein is clear. And so as you add base to it, you start to get this pink color, and eventually the base, or the product turns completely pink, telling you that you've gone actually past neutral, but we'll just say to neutral. You've neutralized the acid with the base, okay? And all you have to do is look at the burette and see, okay, here's how many milliliters of base were required to neutralize this many milliliters of acid, and then we can do some simple stoichiometry to figure out what the concentration of that unknown acid in the flask was. So that's kind of what it looks like. If you don't follow that, well, we don't really have time to do the lab anyway, but at least you've seen it. So let's talk about doing the math. Okay, so it says, what is the molarity of sulfuric acid if 24.5 milliliters of it are needed to neutralize 40 milliliters, 0.55 molar potassium hydroxide? So go ahead and pause now and see if you can set up that balanced equation for the neutralization. Okay, so that's what our balanced equation is going to look like. Just neutralization reaction, kind of like the ones that we just looked at. All right, so then the next step is going to be, I've got some stuff that I can draw out of the question and kind of label here. We've got sulfuric acid, we've got 24.5 milliliters of it. Gonna write that down. We've got 40 milliliters of the KOH, and we also know the molarity of the KOH is 0.550. Okay, and then we want to know what is the molarity of the sulfuric acid, so I'm going to say maybe question mark molar H2SO4. Okay, so let's talk about how we can sort of problem solve here. We want to know the molarity of H2SO4, so the definition of molarity is just moles per liter, right? So it's going to be moles over liters. And we actually don't have 1 liter of H2SO4, we have 24.5 milliliters. So one thing we could probably do is just go ahead and plug in the volume on the bottom of my molarity equation. So 24.5 milliliters divided by 1,000 would give me liters. So 0.0245. So I already have half of my molarity. I have the volume. I just need to know the moles. And so we've already used this bit of information. So let's see if we can use these other 2 bits, the volume and concentration, along with the balanced equation, to figure out how many moles of H2SO4 we have, because if we can do that, then we know the molarity. So what I do is I always start with the volume of the solution that we know the concentration of. So in this case, we know that we have 40 milliliters of KOH. All right, so that is going to go over 1. And then I'm going to go from milliliters to liters, and that's 1 over 1,000. The reason I'm doing that is because the next step is going to be to take it to moles. Because in order for me to get to moles of H2SO4, I guess I should have planned the problem out before I started. Let me do that up above. So we want to get to moles of H2SO4. We can get there from moles of something else in the balanced equation, which in this case, that something else would be KOH, right? And to get to moles of KOH, normally I would say that I would get there from grams. There we go. Normally I would say that I would get there from grams, but because this is an aqueous solution, I'm going to get there from liters. Okay? And I'm not directly given liters, but I am given milliliters. So there's a plan that I'm following. And right now I'm already doing step 1, so milliliters to liters of KOH. Then from liters of KOH, I should be able to go to moles using what? Using the molarity, right? So right here, 0.550 molar potassium hydroxide means that that's how many moles I have per 1 liter, right? And then from moles of KOH, it's just simple. This is where the balanced equation comes in, right? So from moles of KOH, I'm going to go to moles of sulfuric acid. And from the balanced equation, it looks like that is a 1:2 ratio. And so then we get out our calculator, and I got 0.011 moles of H2SO4. And then I'm going to go ahead and just bring this down. So way back here, we said that if we could find our moles, we would just put it over the liters, and that would give us our molarity. So I'm going to go ahead and do that. I'm going to take my 0.0245 liters and just divide that. And so I get 0.44897,959, and it looks like 3 sig figs, so 0.449 molar, this is moles over liters, H2SO4. So that is my unknown concentration. Now, it's always a good idea to check just to make sure, of course, do a mental check. Does that make sense? Yeah, I mean, it's in the range of my other molarity, which it doesn't necessarily have to be in the range, but it's not like it's not like off by a power of 100 or something like that. And so that answer does make a bit of sense. All right, let's try another one. If so, 58.5 milliliters of aluminum hydroxide are needed to neutralize 73.6 milliliters of 0.0850 molar carbonic acid. Find the concentration of the aluminum hydroxide. Sorry, there it is. So let's go ahead and see if you can set up that neutralization equation. Okay, so there you go. A little bit more balancing this time because we had a +3 and a -2 on our 2 ions that make up that salt. Okay, so find the concentration of the aluminum hydroxide this time. Go ahead and write down your knowns. Okay, so that's what we know, and that's what we're looking for, molarity of aluminum hydroxide. So go ahead and see if you can set up the problem and solve it. Don't forget that we're looking for moles of aluminum hydroxide using the stoichiometry, and then we're going to divide it by our liters. And of course, our milliliters always have to be converted to liters. So see if you can work through this one. All right, there we go. And so we got 0.0713 molar aluminum hydroxide. A couple things. Obviously, make sure, just like the previous problem, that we start with the volume of the known solution. And the known solution is the one that we know the molarity of. So we started with 73.6 milliliters of H2CO3. We converted that to liters and then to moles using the molarity, and then we went to moles using the balanced equation of aluminum hydroxide. I got 0.00417, and then I divided it by my liters. And don't forget that your liters, your volume was given to you in milliliters, so I divided by 1,000 before I did my division for molarity. Okay, one last problem type. Okay, so this one is going to be a little bit different in that it is asking you for the volume, and it's giving you both molarities. But let's start off with the balanced neutralization reaction. Okay, so there is our balanced equation, and then I went ahead and wrote down my givens as well. Now we're going to start this problem out just like the previous two. The difference is we're not looking for molarity. We're given molarity, and we're looking for volume. So we're not going to be doing stoichiometry and then dividing like we did in the previous two problems to get molarity. We're going to do stoichiometry all the way through. So we're still starting with our volume of our known substance, which in this case is the base, the barium hydroxide. Could be the acid, could be the base, that part doesn't really matter. So see if you can go ahead and take volume of the base all the way to moles of the acid, and stop there. Okay, so I asked you to stop there because once we get to moles of HCl, normally we would be dividing it by the liters of HCl. Well, we don't know the liters of HCl, but we do know the molarity of HCl. So we're actually going to tack on another stoichiometric step where we go from moles of HCl, which is where we are right now, to liters. And because we're given the molarity, we can actually just plug that in here. So we're told that it's 0.75 molar HCl, so 0.75 moles per 1 liter. And then the last step is going to be 1 liter course of anything, because we're asked for milliliters, is 1,000 milliliters. And now we're ready to get out the calculator. All right, I got 496, which is a big number, but we used a relatively large volume of barium hydroxide plus the 2-to-1 ratio in the balanced equation from HCl to barium hydroxide, so that kind of makes sense. This one's actually kind of a weird one because of sig figs. We only need 2, so really I'm going to call this 500, or 5.0 times 10 to the second. Would give me my 2 sig figs. Or you can do the goofy little repeating sign that also works for 2 sig figs in this case. All right, guys, and that, due largely to circumstances beyond our control, is chemistry. We're done. Make sure again that you get this assignment and any other late ones due by Tuesday. Honestly, at 5% for e-learning, if you've got an 85% or something like that, and you have a few missing assignments, I wouldn't stress out too much, because the e-learning is probably not gonna affect your grade too much. But certainly, if you have a borderline grade, or if you think you even might need those points, make sure that you have everything turned in by Tuesday morning, so I have time to put everything in. And if I don't talk to you, I probably will post a Zoom session for early next week for questions about this assignment, maybe Monday at some point. But if I don't talk to you then, everybody have a great summer, and hopefully we'll see you guys back in school in August.